3.2, the repeated cubing technique. We learned repeated squaring technique. So now you can, just easily generalize it to another special case, repeated cubing case. All right, the same question. So when we evaluate general polynomial, but here we know we need to consider the monomial case, right? That's the special monomial case. Okay, yeah, x to the nth. Remember, at the end of the repeated squaring, that video, I asked you one question. Is that repeated squaring technique optimal or not? Here we can get the answer. Yeah. Sometimes it is optimal, sometimes it is not optimal. So here we will see that. Yeah. All right. Yeah. Here, let me start with a simple example. Okay. All right. Yeah. First, examples. First, n equals 9. How about that? N equals 9. Yeah. If we use the repeated squaring technique. Yeah. First, we use repeated squaring. What is the answer, right? Yeah, because 9 can be written as 8 plus 1, right? Power of 2. Yeah. So you can see if we do x to the 9th in repeated squaring, and we know repeated squaring, we need 3 multiplications plus 1 here. So the answer 4. How about that? The answer equals 4. Yeah. All right, so now I like to do it in a different way. Yeah. Here, the reason is because 9 is a special number, right? Yeah. 3 squared equals 9. Yeah. Can we use the cube operation, not squaring, not square operation, the cube operation? Yeah. So that's another possible way we can try. We want to see if we can get a better solution or, worse solution, right? Yeah. All right. So x to the 9, yeah, we can write it as x cubed times x cubed times x cubed 3 times. 3 times. Okay. Yeah. 1 multiplication here, 1 multiplication here. But in order to calculate x cubed, how many multiplications do we need? Also, 1 here, 1 here. Okay? So the total, 1, 2, 3, 4. The total, the answer also equal to 4, right? So here you can see repeated cubing, repeated squaring, same answer, right? Yeah. For this number, the same solution. We get the same number as the answer, but just for this special case. We cannot say we always get the same answer. We cannot say that, right? Yeah. So we need to apply these 2 methods on another different n and see if they give us different answers. Yeah. So let's try another one. Yeah. All right. Here, before we try, so let's think about what kind of special number can give us different answers. So we want to get different answers. Yeah. Same answers, no improvement. So we want to see different answers. Yeah. All right. Yeah. Now, so let's recall our repeated squaring method another time. Okay. Yeah. So let's recall repeated squaring technique. When this method performs the best, when is this method performs the best? Okay, yeah. When this method performs at its best. Yeah. When n equals power of 2. So this method performs the best. Yeah. Similarly, yeah, can we make similar analogy? Repeated cubing, when this method performs at its best, right? Yeah. This time should be power of 3, right? Yeah. Based on the, logic, yeah. Power of 3, yeah. Yeah. Because for different special numbers, the different techniques can take advantage of that special numbers, can do better or, worse, yeah. All right, so based on this kind of analysis, now we want to find a number that favors repeated cubing, not favoring repeated squaring. Okay, all right. So here, let us consider this number, power of 3, right? Favoring repeated cubing. Okay, yeah. So 3 cubed, how about that? Equals 27. 27, because it's not a power of 2, so it won't favor repeated squaring technique. Yeah, so think about this special case. Yeah. So let us apply repeated squaring first. And to get our first answer number, all right, yeah. 27 equals, break it into sum of power of 2. So 16 plus 11, right? 8 plus 3, right? So 8 plus 3, 2 plus 1. Yeah. All right. Yeah. When we write this way, x times x squared times x 8 times x to the 16th, right? Yeah. In order to do multiplications, because when we do this one, we need 4 multiplications, right? But after we do x to the 16th, it covers all the operands we need for the smaller power of 2 forms. Yeah. Then, other than the 4, 1, 1, together, 4 plus 2, oh, sorry, and then this one, right? Yeah, because this dot, second dot, third dot, yeah. So the answer should be 7, right? By repeated squaring, we get the answer 7. Yeah. All right. Now we want to look at the repeated cubing, but this time we can take advantage of the structure, cube structure. Yeah. Hope we can do better than 7. Answer number. Yeah. All right. So now, let's try repeated cubing here. All right. Now, this time x to the, here x to the 27th. All right. So now this time x to the 9th, x to the 9th, x to the 9th. All right. How many do we need when we calculate x to the 9th in the previous slide? We did it before, right? Think about that. Yeah, we did that before. Okay. Is that 4? Yeah. Because x cubed, we need 2. Then another cube, another 2, right? 2 plus 2, we get 4. Yeah. After this 4, 1 multiplication, 1 multiplication, total. So this case, the answer equals 6. How about that? So this second answer less than the first one. So we get an example. We get the special example for which the repeated cubing technique performs better than the repeated squaring technique. Okay? Yes. So you can see, yeah, for different n numbers, these two techniques sometimes give us same answer, sometimes different answers. For the different answer case, sometimes repeated squaring performs better, sometimes repeated cubing performs better, depends on the structure of your numbers. Yeah. So the structure, if the structure can take advantage of more power of 2, then repeat squaring performs better. If the structure can take advantage more for the power of 3, then the repeat cubing performs better. Okay, so that is the conclusion. Yeah. All right, so let me finish the D.2 video right here.